Next question, calculate the wavelengths of the first and limiting lines. You already know the formula, or at least you should know the formula, how to calculate the wavelength in Balmer series, but you need to understand first and limiting. First line in Balmer series is that from any higher orbit, it should drop to second orbit. This is Balmer transition. This is Balmer transition. All these are Balmer transition because these are at n equals to 2. N equals to 2 is Balmer. N equals to 1, n equals to 3, 4, 5, etc. So Lyman series here, Gaussian, bracket, and font. For 2, it is Balmer. So if first line is said, it means it is the first transition, nearest transition. So this is the first line. It means first transition will be from n equals to 3 to n equals to 2. And the limiting transition is the transition from infinity. So if it is from n equals to infinity to 2, that will be limiting. So you know what n1 you need to use here. Wavelength will remain positive. For wavelength, you will get from wave number, and wave number I have already told you that in wave number n1 is always less than n2. So that's why for wave number I was taking n1 as 2, n2 equals to 3, and for limiting n1 equals to 2, n2 equals to infinity. After that, you know the formula. Okay.
Sir, can you explain what means limiting lines?
Limiting line means limiting, no, not limiting lines. It is first and limiting lines. That's why S is there, because we are considering two. Otherwise, it is limiting line only. And
Okay,
limiting
sir.
line is that line which corresponds to transition from n equals to infinity to n equals to 2. In this case, Balmer series. In case of Lyman series, it will be from n equals to infinity to n equals to 1, because Lyman series corresponds to first orbit transition. Transition from any other
Okay,
higher
sir.
orbit to first. For Balmer
Okay, sir.
series, it is written, it is from infinity to 2. So first case is for first line. First line is from just higher orbit. Just higher orbit than 2 is 3. So substitute these values in the formula for wave number. Substitute the values and get the wave number. But wave number is not required. Wavelength is asked. So 1 by lambda is nu bar. From that, you will calculate the wavelength.
So,
Yes.
so what if the question was calculated in Humphrey.
You are barely audible. There is a lot of noise.
So what if the question was calculated by Humphrey?
Is anybody else able to listen or understand what Vedanta is saying?
No, sir, is
The
my feeling a
same
lot
is
of
happening.
disturbance.
Okay. Vedanta, you can write in the chat box. What is your query? Humphrey series is from JEE perspective. This is something when I was talking about that in theory class. That is not for CBSC. That corresponds to all transitions at n equals to 6. JEE and NEET perspective only. Similarly for limiting line, because for limiting line now you know it means from n equals to infinity to corresponding in Balmer series, the reference is 2. So from infinity to 2. From infinity to 2, but remember for wave number, this will always be n1, this will always be n2. So infinity to 2, substitute the values, get the value of 1 by lambda. From this, you can get the value of lambda. wavelength has been asked. Next question. Calculate the wavelength of a spectral line in Lyman series corresponding to N2 equals to 3. Lyman series means,
So, matlab 3 to 1.
yes, that's it. So Lyman series means N1 is 1, N2 is 3. So initial is 1, final is 3, substitute the values, get the answer. Again, wavelength is asked. From here, you get 1 by lambda. Reciprocal of that will give you lambda. So questions are easy. You just need to know that Lyman series means N1, 1.
Sir,
Yes.
so what is this 1.097 into 10 to the power 7?
This is Rydberg's constant. So for that, you need to remember the formula that the wave number is given by RH 1 by N1 square minus 1 by N2 square.
And so the value of RH is different from other values for this specific formula.
Yes. For wave number, it is either you say 109677 if you are
Per
calculating
centimeter.
this wave number in centimeter inverse, or 1.097 into 10 to the power 7 if you are calculating wave number per meter. So that is something you have to memorize. Rydberg constant. Then it is only calculation. So if you can just understand the levels corresponding to Lyman series, Palmer series, Paschen, bracket, fund, and the related formulas, it is just calculation afterwards. Nothing else. Next question. In Rydberg equation, a spectral line corresponds to N1 equals to 3, N2 equals to 5. Calculate the wavelength and frequency of the spectral line. Yes, your question is the number of spectral lines different in bonded atom and isolated atoms? We are talking about isolated atoms only. Bohr's model is not able to explain anything related to bonded atoms. Okay, that's why this theory failed, because it could not explain the formation of molecules by atoms. So whatever we are talking about atom in its free state, isolated free state.
But the formula of spectral lines that you told in the previous class, so that was for isolated atom.
Yes, that was for isolated hydrogen atom or hydrogen-like species. So the first one is calculate the wavelength and frequency of this spectral line. You know the formula. For wavelength, you will use wave number formula. And then frequency, you can calculate nu equals to C by lambda. So once you have calculated lambda, you will use this formula. Lambda, you know, you have been using this formula. This one is known as Rydberg equation also. Wave number equation is also termed as Rydberg equation. That's why it is written here, Rydberg equation. So as we have done, substitute the values. The only point here is whenever it is given as N1, 3, N2 equals to 5. So you might consider that whether the transition is from N1 to N to 3 to 5 or 5 to 3. You will consider that one as, for example, here it is written, which spectral series this line belongs to. You will always consider the lower one.
So Paschen in this case.
Paschen in this case, right? It can't be 5. The reason is, if you remember, I had drawn the diagram. The transition is always from higher to lower. So if I say Paschen series or Balmer series, for example, I say Balmer series, then I will consider transitions from higher. There will never be any transition from lower one. No, only higher, okay, or to higher. It means lower bound will decide the series, not these ones, not this one, not this one, not this one. Only lower bound will decide series. So here it is 3. So when it is 3 here, you will consider this as lower bound, 3, n equals to 3.
Sir,
All-
does Humphrey series come just after Bradet series?
just after fund series.
Oh, okay, sir.
It means this will decide, lower bound will decide the series. So in this case, it will be Partian because N1 is 3 or lower bound is 3. So whether transition is from 3 to 5 or from 5 to 3, these both are partial. The only difference will be the sign of the energy. If it is from 3 to 5, then energy is positive because energy is given. Energy is given means energy is absorbed by the atom. If it is from 5 to 3, then energy is released. That is the only difference. Same energy will be released, equal energy. Whatever was absorbed, the same energy will be released. Here it is absorbed energy will be positive. When it is released, energy is negative. Energy positive, energy negative when released. That is the only difference. Okay? Lower bound will always decide the series. So wavelength and frequency, you will calculate using N1 and 2. Series, you will calculate from lower bound, which is 3, Partian series. In which region of electromagnetic spectrum will this line fall? Now, Partian bracket fund all fall to infrared regions. So because we have identified, so remember why I am using here 109677 because I am using per centimeter. So that's why. If you would have used per meter, then it would have been 1.097 into 10 power 7. So you calculated lambda, you calculated the frequency also. You said it is Partian series, and Partian series is in infrared region. Lyman series, ultraviolet region. Balmer series, visible region. All three other Partian bracket fund, infrared.
सर कौन कौन सी स्पेक्ट्रल लाइन इंफ्रारेड में लाई करती हैं?
Infrared region, what do you mean by? Okay. Not lines. All lines in Partian bracket fund. All. Whatever transition is in this region, that will be infrared region. Okay. And one more thing I had asked you to memorize the wavelengths and frequencies related to the specific regions. So make sure that you extract 10 to 15 minutes and do that. Next question. The wavelength of first spectral line in the Balmer series is 6561 angstrom. Calculate the wavelength of the second spectral line. You already know what first and second spectral lines mean.
Yes,
And
sir.
we are talking about Balmer series.
Yes.
Balmer series means for first transition is from n equals to 3 to n equals to
2.
Okay, transition. Okay. For wavelengths, obviously you will consider n1 as 2, n2 as 3. For second transition, it will be n1 2, n2 4. 1, 2, 3, 4, 5.
सर ये वाला पार्ट नहीं समझ आया कैसे आपने इन्हें डिसाइड किया?
Were you able to understand this diagram when I explained?
यस सर.
So this is first from the nearest. From n equals to 3 to n equals to 2 is first. Above you have n equals to 4. From n equals to 4 to second, it is second. And so on. Is this clear or not?
Sir, how will we use this 6561 angstrom in for the second part, sir?
I'm
Which
coming
is
to that. I'm coming to that.
okay.
First, it should be clear that first, second, third, what I mean by that. First line is always from just above orbit. Okay, just above. and we are talking about Balmer series. So for Balmer series, the base is n equals to 2. All transitions will be on n equals to 2. So if the transition is from n equals to 3, it will be first line. If transition is from n equals to 4, it will be second line. If transition is from n equals to 5, it will be third line, and so on. If it is from n equals to infinity, it will be limiting line. Is that clear now?
Yes, sir.
Yes.
The only difference will be if instead of Balmer, I say Partian, then all transitions will be on equals n equals to 3. For Partian, this will be the diagram. So from 4 to 3 will be first, from 5 to 3 will be second, and so on. And from infinity to 3 will be limiting line. Yeah. Okay, now good question that how we will use this in second part, right? You might be asked this question even if this part is not given. Calculate the wavelength of the second spectral line in Balmer series, because you can use 1 by lambda equals to nu bar equals to RH 106, sorry, 109677. 1 by, for second line, it will be N1
2 square minus
and
4
2
square.
equals to 4. Yes, 1 by 2 square
Yes.
minus 1 by 4 square. And per centimeter. You can get the answer. Okay? You can get the wave number and then wavelength. Yes, in this question, it is given because you are not expected in this question to know RH. So here you will write RH. 1 by lambda is given by nu bar equals to RH 1 by n1 square minus 1 by n2 square. Let it be per meter because conversion from angstrom to meter will be easier. Now, question says for first spectral line, lambda is given. For first spectral line, n1 will be always 2, n2 in this case will be 3. Substitute these values. 1 by 6561 into 10 to the power minus 10, we converted it into meter, will be RH 1 by n1 square minus 1 by n2 square per meter. So from here you got 1 by 6561 into 10 to the power minus 10 equals to RH 1 by 4 minus 1 by 9, 36, 9 by, so 5 by 36. Let it be first. Now use this case, second case. For second spectral line, N1 will always be 2 in case of Balmer series, but N2 will become 4 now. So lambda is unknown, write it lambda 2, RH 1 by N1 square minus 1 by N2 square, 4 square. That is, you will get 1 by lambda 2 equals to 1 by 4 minus 1 by 16, that is RH 3 by 16. Now 1 and 2 you can divide. RH will get cancelled. When you divide RH and RH will get cancelled and you will get the only unknown lambda 2. Remember lambda 2 here you will get in per meter. You will again convert it into angstrom. Lambda will be in meters, you will again convert it to angstrom. To convert meter into angstrom, you will multiply by 10 to the power 10. So it means it will be this divided by 1 by lambda 2, which will effectively be lambda 2 divided by 6561. So it will be lambda 2 divided by 6561 into 10 to the power minus 10 equals to 5 by 36 divided by 3 by 16. Divided by 3 by 16 means into 16.
Into 16 by 2.
You can solve it now and get the value of lambda 2. When you solve, you will get lambda 2 as 4860 angstrom. Now we need to consider limitations of Bose model, why it failed. Having said that it failed, it is still used for explaining color in the compounds. Okay. In many cases, we will still be using Bose model to explain why some compounds show color or why some elements show color on the basis of transition to second orbit. Okay. So if the frequency is in Balmer region, we will say it is the element is colored. How it is not able to explain quite a few things. So Bohr's model was unable to explain the spectrum of atoms other than hydrogen and hydrogen-like species. So we talked only hydrogen or hydrogen-like species, nothing else. There should be only one electron. It was also unable to explain a splitting of a spectral line. What happened? And scientists noted that, you know, hydrogen spectrum, I talked about emission spectrum, absorption spectrum, and there on the film, there were some bars. What scientists noted that if there was magnetic or electric field present, then these bars actually got split in two or more bars. So there was a splitting of these bars. Single bar got split into two or three bars. So instead of one, two or three bars, very close to one another, they got split. In both cases, whether magnetic field was there or electric field was there. Magnetic field effect was observed by Zeeman, so that's why that was called Zeeman effect. And electric field effect was observed by Stark, so that's why that is known as Stark effect. Both are similar effects, that in presence of magnetic and electric fields, the spectral lines get split. So splitting of a spectral line takes place in presence of magnetic and electric fields, which this model was not able to explain why it is happening. So it was able to explain why these lines are there, because there were specific frequencies related to specific transitions. For if any transition is from N3 to 2, corresponding to that, there will be one frequency which will be visible. If another transition is from 4 to 2, there will be another specific frequency related to that which will be visible. Okay. When electron moves from higher orbit to lower orbit, it will release energy. So that energy will be visible here. Frequency will be visible here. But splitting of these lines was not able to explain. Okay. It could not explain the ability of atoms to form molecules also. That's why I said that we are talking about only standalone free state atoms. Okay. Isolated atoms only. It was not able to explain anything related to molecules. Even hydrogen molecules, it was not able to explain. So moving further from Bose models, Bose model completes here related questions we will be doing, but that is all about Bose model. What conditions we talked about, what properties and characteristics we talked about. Okay. Now, dual behavior of matter. We talked about dual behavior of electromagnetic radiation. That electromagnetic radiation shows wave nature as well as particle nature. So when we talked about electromagnetic radiation, we said that it can possess wave nature or particle nature. But de Broglie, or the correct pronunciation is de Broglie, okay? Although it is written as de Broglie, it is de Broglie, said that it is not only electromagnetic radiation, it is actually every matter in the world which possesses both wave nature and particle nature. It is only that if it is of very small size, for example, electromagnetic radiation consists of electrons, very small in terms of mass. Okay? And suppose I consider a ball. This will also have both wave nature. If there is a ball hit by cricket bat, for example, so it will have wave nature and particle nature both. But he said that if it is very small, then wave nature will prevail. Wave nature will be much more than particle nature. But if it is, say, a ball of 100 gram or so, here particle nature will prevail. And for that, he gave a formula also of wavelength, calculation of the wavelength depending on the mass and speed. So first understand what I am talking about. I am saying dual behavior. Dual behavior means wave nature as well as particle nature is shown by all objects. It is not only the electromagnetic radiation. That is what de Broglie said. And for that, he gave a formula. De Broglie gave following relationship to calculate the wavelength. And what is wavelength? Wavelength is to depict wave nature. He said that wavelength of any object can be given by lambda equals to h by mv, where mv you know is momentum, so that's why it is written as p. M is the mass of the object, v is the velocity of the object, and h is Planck's constant. Same Planck's constant which we have used. Mass, velocity, and h is Planck's constant. Now try to understand. H is constant. H is not changing. Mass and velocity will change. Only mass and velocity will change. To understand it, the wave nature and particle nature, I am explaining it through questions, examples. Question is, what will be the wavelength of a ball of mass 0.1 kg moving with a velocity of 10 meter per second? Kg is SI unit, meter per second is SI unit, so you don't need to change anything, substitute the values. H is 6.626 into 10 to the power minus 34 joule second, 0.1 kg, 10 meter per second. And when you calculate, you will get lambda equals to 6.626 into 10 power minus 34 meters. You will get it in meters because meter is the SI unit. Mass of an electron is given. If the kinetic energy is this one, calculate the wavelength. So here also you will calculate the wavelength. Okay. You can calculate wavelength by this lambda equals to h by mv. But instead of velocity here, kinetic energy is given. That is the only difference. And you know kinetic energy and velocity are interrelated. Kinetic energy is given by half mv square. Okay. Now there are two ways that you can use kinetic energy and you can get the velocity. At this velocity, you can substitute here to get lambda. because anyway here also you have to calculate wavelength in this question also. So kinetic energy is given. Kinetic energy, from kinetic energy you get velocity, because these are related, and from velocity you get wavelength. But you can use this information intelligently also. Instead of
We can write
substituting the value of V, you multiply both sides by M. So M into kinetic energy equals to half M square V square. From here, you will get the value of M square V square. M square V square will be 2M kinetic energy. You can substitute this value here. Lambda equals to H upon 2M into kinetic energy. That is 6.626 into 10 to the power minus 34 divided by square root 2 into 9.1 into 10 power minus 31. You have to use in kg. And the given kinetic energy 3 into 10 to the power minus 25. And you can simplify this one. Yeah. So there are two ways. Either you first calculate the value of V from here and substitute here, or you substitute the value of MV directly and then get here. So from here, you will get the value of velocity, for example, here calculated, and velocity value substituted, and you got the value of lambda. Next question, calculate the mass with wavelength 3.6 angstrom. If it is photon, photon's velocity will be velocity of light. Photon means photoelectron. Okay. And photoelectrons are present in light.
Light.
Okay. So it means velocity here you will consider as velocity of light, that is 3 into 10 to the power 8 meter per second. H, you know, 6.626 into 10 power minus 34. Lambda, you have calculated 3.6 into 10 power minus 10 meter, converted actually from angstrom to meter. So you used lambda equals to H by mv. From here, m equals to H by lambda v. Substitute all the values, get the answer. And you see, the mass of photon is not same as mass of electron. Here in this case, Heisenberg's uncertainty principle is the next topic. Heisenberg's uncertainty principle actually says why we cannot get the exact velocity of electron and the exact position of electron inside the atom at the same time. Either velocity will not be correct or position will not be correct under a certain range. So that's why uncertainty. There is some error margin which is known as uncertainty when we talk about the value of velocity and position of electron inside the atom. Heisenberg's uncertainty principle states that it is impossible to determine simultaneously, means at the same time, the exact position and exact momentum or velocity. Velocity and momentum are related, so whether you write momentum or velocity, same thing, of an electron inside the atom. Mathematically, he gave an equation based on his experience and experiments. He gave this equation. He said that the uncertainty in position multiplied by uncertainty in momentum will always be greater than equal to h by 4 pi. You need to write and memorize this equation. This will be used to explain few conceptual questions and also in numerical questions. Delta P,
सर इसमें x क्या है?
it is uncertainty in position.
Sir, is it associated to distance?
Yes, I'm explaining. Okay, I'm explaining. uncertainty in momentum delta P means how much different or error there can be in momentum, how much error there can be in exact position of the electron. So what Heisenberg said that suppose this is the atom and there is an electron moving say in this direction. He said that if I want to get exact position of this electron, say x, it is at x distance from some reference point, okay? And what is its velocity? X is position. From coordinates, so if we consider coordinates, we will consider this as origin. Then he said that if we want to calculate their exact values, then it is not possible. And for that, there is reason. I'll tell you what is the reason that we cannot find the exact position and velocity. And rest of the things we will discuss in next class. For that, he gave this equation. First, I'm explaining this equation, and then I'll explain why it is not possible, why Heisenberg said that, okay? And that is applicable only for JEE. In CBSE, it is not given and it will not be asked. So to understand this one, suppose you want to calculate exact position. If you want to calculate exact position, it means this will be 0. For exact position,
Yes, sir. Change will be 0.
okay, yes, error in distance, that is delta x, will be 0. Only then you will be able to find exact position if error is 0. And if it is 0, then delta p will be greater than equal to h by 4 pi delta x. And if delta x is 0, this whole will be infinity. Denominator cannot be 0. If denominator becomes 0, the whole value will become infinity. It means error margin in momentum now is infinity. So if you try to reduce error margin in case of distance, if you try to find exact distance, then delta x will be 0, delta p will become infinity. And if you want to calculate exact value of velocity, suppose I write it like this, p can be written by mv. Delta p will be delta mv, but m is constant, so m will come out of delta. M is not changing, so m delta p. It means delta x into delta v will always be greater than m you have taken to denominator here, m. So mostly you will be using this formula, okay? But also this formula. Now suppose I want to calculate exact velocity. If I want to calculate exact velocity means difference in velocity will be 0. And if this is 0, delta x equals to h by 4 pi m delta v. If it is 0,
So
that
ये
means
infinity हो
this will
जाएगा.
be infinity. Now the error margin in position will be infinity. Means at the same time, you cannot get both
So
exact.
not defined, no?
Yes, in this case, it will be not defined because it will be infinity. So the error margin is infinity. It means you cannot get the exact value of position. So what I mean to say that delta x is written from here. Delta x is written as h by 4 pi m delta v, or delta v is written h by 4 pi m delta x. If you want to reduce any of these, okay, suppose you want to make it 0.0001, then delta x will be too high. Okay, if you want to make it delta v, if you want to make 10 to the power minus 30, okay, delta x will be very high. We will explain it through example. Okay, so I hope that mathematically you can understand if this is very low, this is very high, because these are inversely proportional. Is that clear? Why it is
Yes.
not
Yes,
possible? Right. Now, one reason why Heisenberg said that before I close the class today, because if you want to get the position of anything, how, and you will study in, higher classes, the position of anything, for example, radar, etc., how they get the position of any object is that they send a signal. Suppose here is plane. They send a ray, and then this ray strikes there and comes back. These systems actually analyze the time taken to get back. Okay? From that, they can calculate the distance from the origin. So if it takes more time, it means it is far away. If it takes less time, it means it is closer. And they can exactly calculate the distance based on how much time it takes and what is the speed of light with that. Okay. But in this case, what happens? Suppose you want to calculate, get the exact position of an electron, and electron is here. For that, you will have to send a ray which strikes this electron and comes back. There is no particle available with us which can strike an electron and does not deviate it. All the particles we use are heavier than electron. So even if we send one electron, and if this electron we send from here to check that it strikes and comes back, it will deviate this electron because electron will have same mass. You get object this plane because an electron cannot deviate the plane. It will not disturb the plane, aeroplane. It will not have that much mass. But here, if this electron strikes this electron, it will disturb its trajectory. So because it will disturb its trajectory, we will never get exact information or correct information is not obtained. So both will get disturbed. The electron which strikes here and then comes back, and this electron also. Both the electrons will get disturbed by each other and we will not get the exact position and exact velocity. So that's why it is not possible. The reason is very simple. We do not have the particles lighter than electron, which could attack or strike the electrons and also do not disturb the electron. Is that clear? Why it is not possible to get the exact position and velocity? Or if
Yes,
there is
sir.
any confusion. So it is not possible because the electron inside the atom is disturbed by the signal sent by us. So that's why it is not possible. Otherwise, from CBSE perspective, it is not important. For CBSE perspective, most important inequality related to Heisenberg is this one, which you need to remember. And sometimes if in case of momentum, it is discussed, delta x into delta v greater than equal to h by 4. Always. Okay. Normally, you will use to get the boundary condition. And if you get the boundary condition, you will use equal sign here for calculations. So you will use delta x into delta v equals to h by 4 by m. So this is something, just an example that if uncertainty principle is applied to an object of some mass, say about a milligram. Milligram is 10 to the power minus 6 kilograms. 1 milligram will be equal to 10 to the power minus 3 grams, 10 to the power minus 6 kilograms. So for this, we can calculate this. So h by 4 pi m will be h 4 pi m. This is the value, 10 to the power minus 28. Okay. The value of this obtained is extremely small and is insignificant. Now, if I do the same calculation for electron, I will have 10 to the power minus 4. There is huge difference in 10 power minus 4 and 10 power minus 28 because 10 to the power minus 4, if I divide by 10 to the power minus 28 is 10 to the power 24. Means 10 to the power minus 4 is 10 to the power 24 times bigger than 10 to the power minus 28. This much is the difference. So it therefore means that if one tries to find the exact location of electron, say to an uncertainty of 10 to the power minus 8, then the uncertainty delta V will be given by, I'm doing the same thing which I have already explained basically. I'm saying that, okay, I'm trying to get almost exact position. Almost exact position. Almost exact position means the uncertainty in position should be very low. Delta X should be very, very low. If I substitute this value, very, very low, the value of delta V I got 10 to power 4. And 10 to the power 4 variation in velocity is too high. It is not meter per square, it is meter per second. Means this much uncertainty, it is too high uncertainty in
Sir, I
velocity.
have one doubt, sir. So like here we have used h upon 4 pi according to the given condition we used mass. So sir, will this formula be used everywhere or it is h upon 4 pi only?
This M is from here. So that's what I said. Just if you see the formulas, if you are using delta P, then it is H by 4 pi. Delta
Oh,
P can
okay,
be
sir.
written as H
Yes, sir.
delta MV.
M
Then
delta V,
if
yes,
you
sir.
are using this, then M will be here.
Yes, sir.